Over the course of my life, I've encountered discoveries and ideas that changed how I understand the universe around us. I'd like to share that journey with you. Come walk with me. In the previous episodes, we explored black holes through the lens of general relativity. We followed the story from Einstein and Schwarzschild through the event horizon, and finally to the quantum questions raised by Stephen Hawking. But black holes were really about the limits of our understanding of the universe. For me, one part of that story began more than 50 years ago when I attended a talk given by Kip Thorne at a library in Salt Lake City. At the time, black holes were still the subject of active debate, and Joseph Weber had reported observations that he interpreted as gravitational waves. This was important because Weber's data suggested that black holes were actually quite common in the universe. Today, we know that black holes exist. We know that gravitational waves exist. And the connection between those two ideas has opened a door that few could have imagined at the time. In this final episode of Season 2, I would like to explore how the study of black holes has led to the emergence of gravitational wave astronomy, and why this new way of observing may be the first step toward directly exploring those parts of the universe that are now hidden. When I spoke with Kip Thorne in the early 1970s, the existence of gravitational waves remained unproven. Over the following decades, Thorne became one of the principal architects of the effort to detect them. Working with colleagues at Caltech and elsewhere, he helped lay the foundation for what would become the Laser Interferometer Gravitational Wave Observatory, or LIGO, one of the most sensitive scientific instruments ever built. LIGO consists of two identical observatories separated by nearly 2,000 miles. Each uses laser beams traveling along two perpendicular 4-kilometer arms to measure distortions in space-time that are smaller than 1,000th of the diameter of a proton. Because a true gravitational wave signal should appear in both detectors only a few milliseconds apart, scientists can compare the observations from each facility to distinguish real events from local noise and interference. The payoff came almost immediately. In September 2015, just 2 days after advanced LIGO began observations, and before the instrument had reached its full design sensitivity, both observatories recorded the same signal only milliseconds apart. The source was the merger of two black holes more than 1 billion light years from Earth. For the first time, humanity had directly detected gravitational waves. As remarkable as this achievement was, LIGO could observe only a limited portion of the gravitational wave spectrum. Events such as merging black holes and neutron stars produce relatively short wavelengths that fall within LIGO's range. Some of the largest structures in the universe are expected to produce gravitational waves with wavelengths far too long for LIGO to detect. To observe these longer wavelengths, astronomers turn to an unlikely tool. Pulsars are neutron stars in the Milky Way that can rotate hundreds of times each second while emitting beams of radio energy. Each time the beam sweeps past the Earth, we observe a pulse. The remarkable stability of these pulses allows some pulsars to rival the precision of the best atomic clocks on Earth. Pulsar timing arrays are only one part of this emerging field. Future observatories such as the Laser Interferometer, Space Antenna, or LISA, and the Square Kilometre Array, or SKA, are expected to extend gravitational wave observations into wavelength ranges that are difficult or impossible to observe today. Everything we know about the universe has come from observing only a small fraction of what appears to exist. Gravitational wave astronomy is providing an entirely new way to explore that universe. As new observatories come online and existing ones become more capable, we may finally begin to directly observe regions of reality that have remained hidden from us until now. One of the truisms I introduced at the beginning of this channel was simple. If you look somewhere you have never looked before, don't be surprised if you see something you have never seen before. In our next season, we will leave the depths of space and return to Earth as we explore plate tectonics, continental drift, and how I first became aware of this remarkable field of science. So, come walk with me.